about this quiz. I will send you the results, okay, after we finish our lecture. So you will see them in kind of some table where you can see your name and where you can see the percent of right answers and in which question you have the error, okay? Okay, so let's stop here and start our lecture. So,
I'm sorry, could you start the recording, please?
yeah, I did this. You can see that this lecture is recorded. Okay, so today we finally start our discussion about the multiple regression models. So you should remember that previous time we talked only about the simple regression models where we have only one independent variable, but multiple regression analysis, we can say that this is just an extension of simple regression analysis if we want to cover some cases in which the dependent variable is hypothesis to depend on more than one explanatory variable. And of course, in real life, the real processes we can describe with several factors. We first of all read the theory and find which factors will affect our dependent variable. And of course, in most of the theoretical models, you can find that your dependent variable, y, in general terms, yeah, depends on different factors. But anyway, much of the analysis of multiple regression analysis will be just a straightforward extension of the simple regression model. But we will discuss some new problems. The first problem, we need to distinguish effects among different variables. And the second the problem that we need to discuss, that how can we tackle the problem of model specification? And also we have to decide which variables should be included in the regression equation and which should be excluded from our econometric equation. And in most cases, we will discuss all the multiple regression examples, use the basic case where you have only two independent variables, only two explanatory variables. Because, I mean, our theory about the multiple regression analysis. Because in other case, when you have more than two independent variables, the notation of the models and formulas will be really very complicated, and it's better to use matrix notation. So in the appendices of Stocker-Watson, your basic book, student book, you can find the examples with the matrix notation and the ordinal least squares method in matrix notation. So if you want to take a look at this theory, please find this information in Stocker-Watson. But again, the theory and all the assumptions and all the estimations will be the same that we will discuss today. So why in most cases we use multiple regression models? It's obvious, yes, that if we add more factors, relative factors, not any factors, if you add more factors to your model that could explain your dependent variable, then more of the variation in your dependent variable can be explained. And of course, this is our main goal, to predict our dependent variable, to explain the variation in our y. And because of this, multiple regression model is still one of the widely used vehicle for empirical analysis in economics, in business, and in other sciences, not only in economics, of course. And the method of ordinal least squares is popular, used for estimating the parameters of multiple regression analysis. Again, I want to stress that the ordinal least squares mechanically is the same as in the simple regression model, but we discuss some details. So we start our lecture with the discussion of the admitted variable bias problem. This is why we need to use multiple regression model in most of the cases, because of admitted variable bias. And also, we discuss after this, the linear regression model with multiple regressors. How can we check if our model, let's say, good or bad in general terms? How to interpret our parameters, because the main difference between the simple and multiple regression models is in the interpretation of beta parameters. So let's start with the real simple example. So we collect some cross-sectional data. You can see that this is cross-sectional data because we specify only one period from our sample. About the original startup activity, this is our dependent variable, logarithm of startup activity, and our independent variable, the logarithm of regional GDP, gross domestic product per capita. So in this table, you can see the output of this regression, yeah? And of course, our main interest lies in this row, exactly in this coefficient. So this is the effect of logarithm of gross domestic product per capita on the startup activity, regional startup activity. So you can see that this coefficient is statistically significant due to p-value, confidence interval, and t-statistic. And also you can see that this is the relationship is significant and positive, yeah? So the question here, that is it true that the regional GDP per capita is the only one determinant of the startup activity? This is a rhetorical question, yeah? You can even check that R squared, we discussed that R squared could be a general indicator of model or goodness of fit model, yeah? So even R squared is not very low, 23% of variation in regional startup activity we could explain with the gross domestic product. So of course that we should take into account many other determinants at the regional level that can influence our startup activity. not only GDP per capita, yeah? This is obvious. Because of this, simple regression model is not a really good decision for this case, because we assume that we exclude from this model some other important factors that could explain some variation in the startup activity. And if we assume that we didn't include in our main model some really important factors, we should discuss the problem of omitted variable bias. This is a really very important problem in the regression analysis, because you will see the consequences of this problem. So when you exclude a relevant variable from the model, this is omitted variable bias. And also we can say that we underspecifying the model. So, of course, not in all cases, the problem of excluding some variables could lead to the omitted variable bias. But in most cases, this problem causes our estimators to be biased. You should remember from in the fourth lecture, in the fourth lecture, we discuss what does it mean biased estimator, what does it mean consistent estimator. So if you don't remember, please recall the first lecture, because in this lecture we discussed the assumptions of ordinary least squares method, and the assumptions in the simple and in the multiple regression models are almost the same, except for the multicollinearity problem. So if we have bias estimators of ordinary least squares after the ordinary squares approach, this is a real problem for our model. So let's discuss what does it mean in general. So let's say that our true population regression function looks like this. You can see here I highlighted this equation. So our dependent variable y depends on two factors. Let's say x1 and x2 in general terms, yeah, in general notation. And also we have some error term as usual, because we couldn't include all the variables. So what is omitted variable bias? It means that, first of all, x2 has non-zero effect on your dependent variable. This is the first assumption. And the second assumption, that you omit this variable x2 for some reasons, due to some reasons. And this x2 is correlated with the x1 variable. So let's suppose that our main interest, due to our research question, we have some research question, and due to this research question, our primary interest is in beta 1, because you want to find how x1 factor affect your dependent variable. You even don't interested in the effect of beta 2, yeah, of the effect of x2 on your dependent variable. But again, I want to note and I want to stress that even in this case, if you know that x2 should be included in this model, in the true population regression model, and if you omit this variable, it will be bad. So in order to get unbiased estimator of beta 1, you should run this regression. But due to some, let's say, you ignore this, Or maybe you didn't ignore this, but you didn't have available information about the x2. So you estimate the model excluding x2, and you perform, instead of this model, just this one. You perform just a simple regression of y on x1. And so finally you obtain this estimated equation. So in this case, your beta1, estimated beta1 parameter will be biased. So what does it mean? It means that the expected value of beta1 equals the true beta1 parameter from the simple regression of y on x plus some bias. And this bias, this one, equals beta2 parameter multiplied by some tilde. And this tilde means the slope coefficient from the single variable regression of x2 on x1. Or in other words, it means this tilde is the sample covariance between x1 and x2. So the question is, looking at this equation and looking at the assumption that we just discussed, in which cases there was still no bias if, for example, we omit the variable x2 from this equation? In which case there will still no bias? What do you think?
Maybe when x2 has no effect on
Yeah, right. So the first case, when beta1 will be unbiased, if beta0 has zero, beta2 has zero effect on your dependent variable. Or in other words, when x2 has no effect on your dependent variable. Okay? And the second case, you can find all the clues on this slide. What will be the other situation in which your beta1 will be still unbiased if you didn't include the x2 variable in your model? The first case, when x2 doesn't appear in the true model. And the second case?
Maybe when x1 and x2 are uncorrelated?
Yeah, so the second case, when the sample covariance between x1 and x2 equals 0, yeah? So x1 and x2 will be uncorrelated. You're right. So please read the first point here. Okay. So the problem with the omitted variable bias is if you exclude from your true model x2, and this x2 variable is correlated with the x1, and also this variable has no zero effect on your dependent variable. The problem that, for example, if you decide to increase your sample size, so if you decide to collect more data, it doesn't help you because the bias could not be eliminated with the increasing sample size. This is bad news. But also, the bias depends on the correlation between x1 and x2. In our example, yeah, here could be not one subscript or two subscript. Here could be any other numbers. It doesn't matter. We discussed the emitted variable bias on this example. So if the correlation between the independent variables is large, the bias is also large. So if we have if you know that the bias depends on the combination of correlation between independent variables and the sign, positive or negative, size and sign of your beta 2, yeah, you can obtain 4 options. So if the correlation between independent variables is positive and beta 2 is positive, the bias of your estimated parameter will be positive. If the correlation is positive, but the sign of, let's say, expected sign, yeah, we don't know the true sign, but we could assume, we could say that we expect positive or negative sign of the beta 2 parameters, parameter that we exclude from our model, yeah, is negative, so the bias will be also negative. If the correlation is negative, but the sign of the emitted variable is positive, the bias will be negative. And if correlation is negative and the expected sign of beta 2 is negative, the bias will be positive. So this is 4 combinations that we can obtain if we want to guess about the emitted variable bias sign. But let's practice with some example. So I think that this is really actual example, relevant example to our situation, unfortunately. But let's say that you have a true population model where the dependent variable is some survival cases. And true population model includes 2 independent or 2 explanatory variables. One of them is health, and the second one is hospitalization cases. But due to some reasons, we calculate the simple regression model. Let's say that we didn't find any information about the health, but we find only information about the hospitalization cases. So our estimated models is this one. Where you obtain beta 0, you intercept beta 1, some coefficient, on hospitalization cases. So the question is, which statement is correct? The first one, the second one, third one, or the last one? And if you want to find the right answer among this one, so you need to think about two things. The first one about the correlation, positive or negative correlation between this variable and this variable. Yes? And the second thing that you need to assume some effect of this variable, this omitted variable, yeah, on your dependent variable. So the effect of health on your dependent variable survival cases. So here, I can say that if the respondent has better health, the value of this variable will be higher. So again, let's take a look at these combinations of correlation and the sign of omitted variable coefficient, and provide your suggestion. What do you think? Which one is correct statement? Any guess? What do you think?
Maybe first one.
Maybe which one?
First one.
Okay, you're right, but why?
Because if we consider also health, their survival will be less. So this is why expected value should be smaller than what we got.
Yeah, you're right. In general, we have a downward bias. The first answer is right. So let's discuss for other students. Which logic should you follow when you want to answer such kind of questions? So we have underspecified model, this one, and our true model, this one. So in our case, we can assume, yes, that people with better health have better chances to survive on average. This is our first idea. And the second idea, that the average hospitalization cases is probably negatively correlated with the health. So beta 1 here, we have a negative bias. Or in other words, we can say that beta 1 has downward bias. And the true population coefficient will be greater than the expected value of our estimated coefficient. Or in other words, again, yeah, I want to repeat that in this case, we have a negative bias or downward bias. And the ordinary least squares estimates from the simple regression instead of this one, instead of this model, average smaller or average too small if we compare with the true population model. So the answer was right, but please remember about this logic. You can read this logic here about the correlation between the independent variables and about the effect of the omitted variable of health on the dependent variable. Okay, do you have any questions? This is really very important. The admitted variable bias is important topic in any kind of models, not only in this multiple regression models of when we use ordinary least squares method. This is basic things that about which you should remember in every model. Okay, I hope that your silence is a sign of that you understand this point. So the second thing about the admitted variable bias that is really very important, that also you should think about the size of this bias. So the magnitude or the size of this bias matters too. For example, if you assume that the bias will be, let's say, small, in this case, maybe the problem of this bias will not be very high. Yeah, will be important. So if you miss some important confounder in other situation, your estimates will be biased and inconsistent. And this is a real problem because if you remember about one of the main assumptions about the ordinary least squares method, yeah, one of the main assumptions that your error term should be uncorrelated with the independent variable or independent variables in your model. And because of this, you should avoid admitted variable bias. And of course, in general cases, it's hard to discern with more than two covariates, the bias is more difficult to discern. And because it depends on all the pairwise correlation between the independent variables. But if you want to avoid this problem, of course, you need to include in your model the appropriate variables. So in general case, when you have two independent variables, x1 and x2, the model looks like this. So you can see that the notation of the model is very similar to the simple regression case, yeah? They look the same. So, and also the terminology for multiple regression model is similar to for the simple regression case. Just as in simple regression, the variable, this one here, is the error term or disturbance or some stochastic term. So it contains factors other than x1 and x2 that affect your dependent variable. Of course, there will always be some factors, some things that we cannot include, and these factors contained in this error term. Okay, and also this is our dependent variable x1 and x2, our independent variables. So the terminology is the same. And also when we use the multiple regression model, we can distinguish the variable of our main interest. Let's say that this is x1, yeah? We want to find the effect of x1 on our dependent variable, and we use x2 variable just to control, just as a control variable in this model. For example, we want to find the effect of education, level of education on the level of wage, and we want this is our main interest, yeah? But we want to control for the gender. and we want to control for age, or we want to control for some other factors, for example, for health or for marital status and so on. But our main interest is how educational level affect the wage level. Okay, I think that this is clear. And also, of course, in the general case, we can use K explanatory variables, but the notation will be the same. We just add some other factors and again add the error term. And the estimated equation will look like this one, where you add head over the dependent variable, your beta parameters, and also you have k explanatory variables. So how can you use the ordinal least squares method? So mechanically, there will be no difference in using the method of ordinal least squares to estimate equations in simple or in multiple regressions. So you still should remember that your main goal is to minimize the sum of squared residuals, this one. The main difference between the simple and multiple regression in ordinal least squares approach is the interpretation, because now in multiple regression model you can use ceteris paribus effect when you interpret the parameters of multiple regression model. What does it mean? We discussed in several minutes. But now let's take a look at this slide. So in general, when you have k regressors, you need to minimize this term, yeah? How can you do this? You need to take the partial derivatives of this term with respect to each parameter. Because of this, you have some linear system that you need to solve. Let's take a look at our basic example when you have only two independent variables, because it's much easier, yeah? Again, I want to repeat that if you have a lot of regressors, if you have k regressors, it's better to use matrix notation when we discuss the ordinal least squares method in multiple regression model. Because of this, let's discuss the same, but in case we have only two independent variables. So your estimated equation looks like this. But how you can obtain beta 0, beta 1, and beta 2? The method of ordinal least squares chooses the estimates to minimize the sum of squared residuals. So the estimates beta 0, beta 1, and beta 2 are chosen simultaneously to make this term minimum. So, or in other words, you can use this notation with the arc mean, yeah, where your parameters are chosen in such manner to minimize this term, yeah. How can you do this? You need to find the partial derivatives. Let's take a look here. You need to find the partial derivatives and then set each partial derivative to 0. to obtain the first order condition. In our case, when we have, let's return to this slide, when we have the model with only two explanatory variables, we assume that you will have free equations, free system of free linear equations, because you have two independent variables, because of these two slopes, and one intercept. So totally you need to take the partial derivative with respect to beta 0, this one. You need to take the second partial derivative with respect to beta 1, and you need to take the third derivative with respect to beta 2. And also, if you want to find the unique solution for this system, you should remember that the number of observations should be greater than the number of your variables, the number of your predictors. And also you remember, I hope that you remember, this is one of the assumptions of the ordinal least squares method. We discussed this. And the second, we also discuss this topic among the ordinal least squares method assumption, that two independent variables should not be linearly correlated, perfectly correlated with each other. In our case, for example, x1 and x2 should be linearly independent, or in other words, they should not be perfectly correlated with each other. We discussed this in case of multicollinearity or perfect collinearity. Okay, this is two assumptions that you need to hold if you need to find the unique solution of this system. And generally speaking, the formulas of beta 0 and beta 1 looks almost the same as in the simple case, in the simple regression case. So this formula for the intercept is almost the same, but we add here one more parameter, and we can obtain these parameters through these formulas, where you can find the covariance between each of the independent variable with the dependent variable, and also find the variance of each independent variable. Then you'll use these formulas and find beta 0, beta 1, and beta 2. Good news that during our course, you don't need to calculate these formulas manually, Stata will do this for you. If we talk about the multiple regression models, but you need to understand the idea and the mechanism behind these formulas. You need to understand how can you obtain them. That this is just the covariance, the difference between the covariance and over the variance minus covariance. Okay, so the main difference, again, let's return to the interpretation. The main difference between the multiple and simple regression models is interpretation of our beta parameters. So you have already learned how to interpret the beta coefficients in the simple regression models, Your interpretation in the linear case, when x1 and y linearly dependent, we interpret this case like the coefficient, let's say beta 1, measures the change in your dependent variable y due to a 1 unit increase in x1. But now you have other variables in your model, yeah? And the interpretation will be, generally speaking, the same, but now we will use ceteris paribus, or holding all other factors fixed, additional formulation. So let's take a look at this. What does it mean? So we can rewrite this equation in this term. So we can obtain the predicted change, delta means change here, in y given the change in x1 and x2. But when we interpret x1, we assume that x2 holding fixed. Or in particular, when x2 is held fixed, the change in x2 equals 0, yeah? Then our interpretation will be the same as in the simple regression model, but we should add that holding x2 fixed. The key point here is when you including x2 in your model, you obtain the coefficient on x1 with the ceteris paribus interpretation. And similarly, logic will be if you interpret x2, the effect of the second variable x2 on your independent variable, but in this case you say that holding x1 fixed. Holding other factors fixed means the same as you said ceteris paribus, okay? This is the same. So we can say that when we holding other factors fixed, we controlled for these factors. So when we fixed x2 and interpret the effect of x1 on our dependent variable, it means that you interpret the effect of x1 on your dependent variable, but you controlled for other variables too, okay? And the power, the real power of multiple regression model is that this model provides this ceteris paribus interpretation, or multiple regression analysis allows us to mimic the ceteris paribus situation. Does it make sense? Is it clear for you? What does it mean? What does it mean, ceteris paribus effect? Any questions? Guys? Georgi, yes. It means that it's clear. Okay. Thank you, Georgi. I hope that for other students it's clear too. But maybe let's say, for example, what does it mean, ceteris paribus? Let's say that we want to conduct not as economic experiment, but we want to conduct experiment how to grow flower seeds. And in this case, you can control the level of water, yeah? You can control the level of light, you can control the temperature. And you have two seeds. And you want to find in which cases the flower grow faster. And you can manually change the level of water, for example, yeah, for to the seeds. But in this case, if you change the level of water and you want to find how the level of water affect the, let's say, speed of how the flower grows, how the flower grows faster, yeah, or slowly, you can control only for one factor. For example, you can manipulate one factor, okay? But other factors such as light, such as temperature, you holding fixed. In real life, with economic data, you can't provide such kind of experiment. Yeah, it's really physically very hard. You need a lot of money, and also in most cases this experiment is not ethical. Yeah, because of this we just use some surveys and conduct some data. We collect data about the let's say some salary. We collect data about some economic and demographic characteristics of respondent and so on. But multiple regression analysis help us to mimic the ceteris paribus situation, the same situation as we just discussed with the experiment with the flower seeds. Okay? So the idea behind this interpretation is the same as we just discussed. What does it mean holding all other factors fixed? So we don't change other factors. We just control on them. And also you can interpret the beta-1 parameter, beta-1 coefficient in terms of residuals. So maybe it will be more obvious if we discuss the effect of beta-1 in residual terms. So residuals here, this one, yeah, this is residuals from the regression where we regress our first independent variable x1 on our second independent variable x2. And then we obtain these residuals and plug in them in this formula. So you can know that the residuals have a zero sample average, and so beta-1 is our usual slope estimate from the simple regression. So the residuals are the part of x1 that is uncorrelated, yes, with x2, because residuals can present us this uncorrelated part of x1 with x2 after the effect of x2 have been partialing out. So you can interpret beta-1 parameter in terms of residuals from the auxiliary regression of x1 on x2. And because of this, again, the interpretation of x1 maybe will be more obvious in these terms. What does it mean holding all other factors fixed? So if we talk about the goodness of fit, again, R squared in general terms could be used as the, let's say, as an indicator of goodness of fit model. So just in simple regression case, we use the same formulas, yeah. We have discussed this formula today in the quiz example. And also you can note that R squared could be presented as the squared correlation coefficient between observed values of y and the fitted values of y from your estimated model. So this formula is also the general formula for simple or for multiple regression case. doesn't matter, yeah? But the main problem with the R squared that every time when you add additional variables in your model, R squared will increase because the sum of the squared residuals will decrease if you add additional explanatory variable in your model. This is the problem. So it means that R squared could not be a very good indicator for the multiple regression models, because in general case, if you compare, for example, simple regression model with multiple regression model, R squared will be high in multiple regression model, even in the case when your additional variable is not appropriate, is not relative, yeah, to your true model. So this is the problem. And because of this, we need to use not the real R squared indicator, but instead of this, you can use adjusted R squared. So you need to adjust R squared by some degrees of freedom. This is the formula that you can use to find the adjusted R squared, or let's say some alternative coefficient of determination. So you can see here that in the numerator, this is just the sum of squared residuals here, but you correct the sum of squared residuals by the degrees of freedom, n minus k, yeah? Number of observation minus the number of parameters or the number of your variables, including the intercept term. And in the denominator, again, you can see the total sum of squares, but corrected by the number of observation minus 1. So in multiple regression models, if you want to compare which, for example, model is better, you can use adjusted R squared. Not as general R squared, but adjusted R squared corrected by the degrees of freedom. And also, I want to note that when you compare several regressions and you use R squared or adjusted R squared, you need to remember that your dependent variable should be the same, yeah, in this regression. In other cases, you can compare these models if your dependent variables are different, yeah. So you can compare R squared and adjusted R squared only in the when your dependent variables are the same. And also you should remember that you can't choose a set of explanatory variables based on the size of R squared or adjusted R squares, because in this case it can lead to nonsensical models. For example, you have seen several regression that had pretty small R squares. And this means that, what does it mean? It means that you haven't accounted for several factors that affect your dependent variable. But this doesn't mean that the factors that you didn't include are correlated with the independent variables. Yes, your model still could be unbiased. So your estimator still could be unbiased. Even if your R squared or even if your adjusted R squared is not very large, the size of this R squared, yeah? Because the real problem is when you doesn't hold the assumption about the zero conditional mean. Biased or unbiased estimators followed from the zero conditional mean assumption. And a small r squared means that the error variance is large relative to the variance of y, which means you may have some hard time precisely estimating the parameters. But even in this case, it could be not a problem for your model, yeah? So if you estimate some model and see that the r squared is not equal, let's say 0.8 or 0.9 or even 0.7, it doesn't mean that your model is bad. It just could mean that you have some problem with the precisely estimating your betas. But also you can compensate this by large sample size. For example, if you have an opportunity to increase your sample size and you hold all the assumptions of the ordinal least squares method, your estimators will be unbiased, maybe not very precise, but unbiased. And if you can increase the sample size, you have enough data, you may be able to precisely estimate the partial effects, even though we have no control for many unobserved factors. Okay? I think that this is main idea that you should remember. Please don't play a game when you want to maximize r squared and you manipulate, or let's say maximize the adjusted r squared and you manipulate with the factors. You want to include a lot of factors and manipulate with the r squared. And also remember about the adjusted r squared, because in this case, adjusted r squared use some kind of penalty when you include a lot of variables in your model, yeah, because degrees of freedom will increase in this case, and adjusted r squared would be even negative. If you remember, our r squared lies in range from 0 to 1, yeah, you remember about this, but your adjusted r squared could be significantly lower than just usual r squared estimate, and also could be negative. And also, you can take a look there at the adjusted r squared in terms of r squared. Maybe this formula is looks better for you than the previous one, because you can use just r squared and then adjust for some degrees of freedom and number of observation. Please remember that in this formula, k is the number of parameters including the intercept term. So all your exponential variables plus the intercept. And also you can find in some books that instead of adjusted r square notation, yeah, in some sources you can find r square with the bar, like this one. It also means adjusted r squared, but different notations. So, and also the adjusted r squared is strictly smaller than our usual coefficient of determination, unless situation when you have only intercept in your model. In this case, adjusted r squares and usual r squared will be the same. Okay, let's stop here. Next lecture, you will have a test, and this test will be assessed And in a lecture, we will continue our discussion about the multiple